Okay, let's get started. So we covered a lot of important things last time, so let's go through a few of them. So we talked about this quantity gamma I. This measures the signed distance from one of our ith data points to the decision boundary. And this distance is signed in that whenever we have a sample for which the label is yi equals 1, we get one sign, and if yi is not equal to 1, we get the other sign. Then we revisited linear separability, and we said that we can think of it as when there exists some b and w parameters such that this inequality holds for all I. So this is the binary label, 1 or minus 1, times the score must be greater or equal to 1. Okay, so the score, again, is positive when yi equals 1, and negative when yi equals minus 1. So you can see that this yi is sort of changing the sign on the score, and it means that the sign-corrected scores are all greater than 1 for all the trained samples. And then we put this definition together with linear separability to say that basically for some b and w or some w that satisfies this, we know that the following holds, that the sign-corrected sign distances are all lower bounded by 1 over the norm of w, which is an important quantity, so we give it a name gamma, and we call it the margin. So if we look at this picture here, we have our linearly separable data, and here we have a w and some b's that give us one of those separating designs. And when you look at the distance, this is the minimum distance from any training point to the boundary, gamma. You can see that this gamma is like a lower bound on all those distances. So those are sort of the math details. And then we also said, from maybe a practical point, that we like that boundary versus a boundary like this, because this boundary gets a lot closer to the training points, meaning that if I have a test point that's maybe a little bit different than a training point, like maybe a test point over here, you can see that this boundary would not be robust. You would make some errors. Whereas this boundary here is in some sense maximally robust because it is as far away as possible from the closest training points. So that's the idea, and basically if this 1 over norm of w gives us this lower bound to the closest training point, and we want that to be maximized, then equivalently we want the norm of w to be minimized while also satisfying this linear separability constraint. So that gave us our first design, which we called the hard margin classifier. So here, we're minimizing the norm of w, or equivalently maximizing that margin, subject to linear separability. And this does exactly what we want it to do whenever the data is linearly separable, which means we can find some b and w that satisfies this constraint. The trouble is that in practice, we often have data sets that are not linearly separable, which means that this formulation is useless because there are no BW pairs that satisfy this for all our training points. So to get around that, we said, let's relax this design a little bit. And in particular, we're going to replace this set of inequalities with a cost function. So to do that, we first looked at those inequalities. They take this form. And then we just moved this to the right side of the equation, which gave us this. And so that means if we can do linear separability, this term here is at most 0 and typically negative for all I. And so we said, why don't we replace this set of inequalities with this cost function that sums over our training the maximum of either 0 or that same number we have over here. And so this way, if we want to minimize that cost, that encourages all of these values here to be less than or equal to 0 if possible. And if that can happen, if our data really is linearly separable, we can drive this cost all the way to 0. On the other hand, if our data is not linearly separable and it's impossible to satisfy this for any B and W, we can still minimize this cost and maybe get as close as possible to linear separability. So that's the idea that gave us the second design, which we can call the soft margin classifier or the support vector classifier. And it looks like this. And so here we have the same term from the hard margin classifier, but now we replace those inequalities with this cost. And the one new thing we had to add is a scalar weight, C. And that weight is used to trade off between the two things in the sum that we're minimizing. And if C is really large, it puts a lot of emphasis on this term, which it basically means that you don't want, if you can prevent violations of these inequalities, you don't want any of them. You put a lot of emphasis on that. And less emphasis on making W small. Remember, making W small is like making the street wide. So if you put a large C there, you're gonna try to make your street as small and not have a lot of XIs in that street or on the wrong side of the street. On the other hand, if you make C really small, then it says you don't care as much about getting positive values here, which means you will possibly get some violations here. And on the other hand, you will try to drive W small, which means you get a wide street. And so we had some pictures here, like with a small C, you get a very wide street. We have a lot of support vectors. These are the points that actually are used to compute the boundary. Those are the points that are in the street or maybe on the wrong side of the street. You can see we have a lot of them. On the other hand, when C is very large, then we want the street to be very narrow. So we have some very narrow street. And there's only a few training vectors or support vectors that influence where that boundary is located. And then here we have like an in-between choice of C. So that means that this C parameter is super important in the performance and design of the classifier, and it's something that we should choose with cross-validation. And one way to think about that choice is through the bias variance trade-off. Basically, when you have a really large C, you have just a few support vectors, which means that this boundary will change a lot if you imagine doing different experiments with different data sets, maybe all generated from the same random sampling scheme. On the other hand, if C is very small, then all those points are affecting the boundary and you get sort of an averaging effect. And if you did many experiments like this, because of that averaging effect, you would find that the boundary doesn't change very much. So over here we have high variance, over here we have low variance. But on the other hand, when you look closely at the boundary here, it's doing a great job in terms of preventing classification errors. It looks like all the points, red and blue, are correctly classified, whereas over here, you can see there's some issues. These red points are incorrectly classified, as are these blue points. So here, essentially, on the left, it is really prioritizing the points closest to the boundary and making sure that it's minimizing the number of errors. But over here, it's sort of trying to make all those points happy, which means the ones close to the boundary are not really determining where that boundary is. And it's actually allowing a certain number of errors on those points. So that's how we can think about the effect of this penalty weight C and the bias variance trade-off and why we need to tune it using cross-validation. Okay, any questions so far? Okay, so those are a lot of the main points. Then we related this new method, rewrote it this way by moving the C over here. And we saw that it's actually quite similar in structure to the L2 regularized logistic regression. Really the main difference is this loss function inside the sum. And when you plot the two of them, you can see the differences. So this is, for the SVC, you have what people call the hinge loss. This plot is when yi equals 1, and it's a plot versus zi. And you can see the hinge loss has this form here. So, when yi zi is greater than 1, then this is less than 0, and the output of this is just going to be 0. So that's why you get this sort of piecewise linear shape like that, whereas logistic loss gives you a smoother shape. And they're both linear with slope approximately 1 over here. They're both close to 0 over here, but they differ in the details. This red one, the logistic one, never goes exactly to 0, meaning all the training points are used to determine the weight and bias, whereas for the SVC, you can see that the only training points which matter are the ones which give us scores over here, and those are the support vectors. So that gives you some of the differences in flavor between logistic regression and the SVC. Okay, any questions on this? Okay. And I think the last thing we talked about was another way that people write the SVC that you might see in some other sources. It's really not that big of a change. Essentially, you take this hinge loss thing and you basically give it a name, xi. And so then you just have xi inside the sum. And then the other thing you need to do is you need to change essentially, yeah, because to handle this max, this puts two different constraints on xi. Number one, xi must be greater than 0, and it also must be greater than this term here. So basically, this gives you a new formulation of the SVC that you can solve using a constrained optimization technique. And also there's an interpretation to these slack variables. The slack variables tell you how much the margin is violated. So if you find that a slack variable is 0, it means that that point is basically outside the street, so it's not one of your support vectors. Or let's say, I guess maybe you could have support vectors right on the edge, in which case they would also have xi equals 0. So xi 0 happens when you're right on the edge of the street or outside the street on the correct side. If you're in the street, like this point or this point, then xi is going to be between 0 and 2. And if you're on the wrong side of the street, it's going to be, so like for a green point, if you're all the way over here, that's going to be greater than 2. And when you're right on the boundary, the slack variable is 1. So anytime the slack variable is greater than 1, that means your point is on the wrong side of the decision boundary and will actually be a classification error. So that's just another way of writing the SVC. Okay, so that's sort of a summary of what we talked about last time. Any questions on any of that? Okay, so just a few more things to talk about with the SVC. What happens if we have more than 2 classes? So in that case, because we're doing linear classification, all our linear classification methods work like this. in the multi-class scenario. Essentially, the B scalar is now replaced by a k-dimensional vector where capital K is the number of classes, and the W vector is now replaced by a matrix where every row gives us the one versus rest weight vector. Basically, like this is class 1 versus the rest, this is class K versus the rest, and so on. So now we need to figure out how to design the B vector and the W matrix, or essentially all those terms there. And there's basically two approaches. One option is just to separately train the first BW pair, the second BW pair, and so on. That's maybe the most straightforward option. That is similar to what we saw in logistic regression as also one of the options there, one versus rest, design pairs of binary classifiers. But in logistic regression, we also talked about jointly designing them using MLR. And here, we can also do a joint design, but it has the name of the Kramer-Singer approach. And it's a little bit more complicated to look at, but basically this is how you do it. And I don't want to get into too many details, except to say that if you look at this in the k equals 2 case, and you do a little bit of analysis, you can find out that this matches the original binary SVC. So basically, it's just a way of generalizing our original binary SVC to more than 2 classes. It is more computationally intense in terms of running the optimization algorithm to do this, but it does work a little bit better in practice than this one versus rest approach. Whether it's worthwhile to use it or not really depends on how much computational power you have and all of that. So these are all things you can play with in the final project if you're working on this. Okay, so that's basically the multi-class SVC. 2 options, one versus rest or this other joint design approach. Okay, any questions on that? Okay, great. So let's just finally talk about a few implementation options in scikit-learn. So, so here we have the SVM is the library we're going to use, and the linear SVC is the method that we've been talking about. And it has various options, like for multi-class, you can do OVR, that's the default, or you can do Kramer-Singer if you want to do joint design. Of course, you have to specify the weight C, just like in logistic regression, and you have to do a decent job of tuning that for this to work best. Another interesting thing is that you have a choice in the loss function. So what we've been talking about would be using the hinge loss, but it turns out that is not the default option. The default option is actually the squared hinge. So let's go back and look at this picture to see why that might be. Okay, so here's the picture of the hinge in blue. So let me see, is Cameron Ailes here? Yeah, so what do you think the squared hinge would look like if you plotted it?
It would be a 0 past that line still, and then would it be more of a quadratic shape?
Yeah, right, so it would go this point, right, because 1 squared is 1. That wouldn't change. 2 squared would become 4. And so basically you would have a half of parabola like that, right? Something like that. Okay, so that's what you would get. Let me be a little more careful down there. And so let me ask, let's see, is Aidan Cooper here? Okay, what about Alex Lucas? Yeah, so what do you think the advantage of the squared hinge might be, and why would that be the default option in sklearn? Okay, so from the perspective of differentiability, that's the hint. Which one is differentiable, which one is not? So is this quadratic one differentiable? Do we know the derivative at every?
Yeah.
Yes, right? But the other one, the blue one, it has that sharp corner, right? So there's no derivative there. So basically thinking back to the last unit, Unit 6, when we talked about optimization methods, we said that if you have differentiable cost functions, you can use gradient-based methods. If you have a non-differentiable cost function, which would be the case with the hinge loss, you cannot use a gradient-based method. You have to use a different type of optimization algorithm that runs slower. And that's actually the motivation here for using this kind of differentiable version of the SVC with the squared hinge loss. Basically, it runs faster. Now, in my experience, it doesn't work as well because you've actually changed the whole design, right? You've like put in this new thing that, yes, it does inherit some behaviors of the SVC in that there still will be support vectors that influence the design and then a bunch of other data samples that don't influence your design. So it retains that flavor of the SVC, but yeah, it has a very different behavior down here, quadratic versus linear. And so, not surprisingly, the results are different. So in my experience, it doesn't work as well, but it runs a lot faster. So just something to be aware of. When you run this, unless you change the default explicitly to loss equals hinge, you're actually going to be running squared hinge, and your results will be different than you might expect. Okay, great. So those are really, otherwise, like since you guys have learned how to use logistic regression, it's like the interface is exactly the same as that. So once you learn these sklearn tools, they're pretty much all the same. So the final result of all this, going back to our data set MNIST, recognizing these handwritten digits, is the accuracy is now 90.7, which is 0.5% better than logistic regression. So, what do you say? After all this effort, is that a little underwhelming? Not so exciting, right? So it's like, yeah, we did all this stuff. And it was basically like 0.5% better. It's not really that exciting, no. So that's actually not the end of the story. To get to the end of the story, we need to think about something else, which is feature transformations. So before we change gears, are there any questions on anything we've talked about so far? Okay, so what I'm going to talk about now is what we will call the support vector machine. And the motivation is like this. So this support vector classifier, if the data is linearly separable, then based on our drawings and stuff, we can see how this is really going to be robust. It's sort of, in some sense, designed in mind when the data is nearly, like linearly separable or nearly so. Maybe there's a few points that are not. But if you have data that's just super far from linearly separable, it's not really clear whether this support vector classifier is really going to have much of an advantage over other methods. And that's, in some sense, just due to the limitations that we have with any linear classification method where they are trying to classify data using a linear boundary. And when you have data that is far from linearly separable, there's absolutely no linear boundary that is going to work for that data set, even remotely well. So, so that sort of motivates us to add something extra to it. And the thing that we're going to add to it that's extra is a feature transformation. And by a feature transformation, we really mean kind of like a pre-processing step. You get your data, your raw features X, and you put them through some function to give you this new set of features, which is typically in a higher dimension. So you start with D features and you get like some number of features that's larger than D. We've actually seen this before. One time we saw it was with polynomial regression. You get a scalar feature, x, right? And then if you want to do dth order polynomial regression, you basically get D new features. You get x squared, x cubed. That's an example of one of these feature transformations that goes from one dimension up to however many you decide, right? And we talked a lot about how to choose the number you decide. We had a whole chapter on model order selection to try to get at that choice. But that's just one example of a feature transformation. You can imagine many, many other examples. Maybe you can exponentiate things, or you can put things through sinusoids, or just, the sky's the limit. You can do anything you want. So we're just talking about some sort of transformation. What you want at the end of the day is that this transformation that you use makes your data linearly separable or closer to linearly separable. And once you do that, then perhaps this SVC is going to start working well. So that's really the big idea here, is feature transformations to enhance linear separability. But there is another kind of piece of the puzzle which has to do with the implementation, which we'll get into the details. But it turns out that the most famous transformations phi actually give an infinite dimensional output. And if you think just about like, okay, how would I deal with an infinite number of features? It's not really clear that we have any way of doing that, because an infinite number of features here would require us to train an infinite number of coefficients in our weight vector W, and we simply can't do that. So it turns out that there's a way around it where instead of formulating this idea directly with this feature transformation phi, we can actually kind of reformulate the problem in a way to actually avoid directly defining phi, but instead working with like pairs of phi x1 and phi x2, and that thing is called the kernel trick. And that gets around the issue of high dimensional features, and we'll see all those details. But basically, this is just sort of like a stylized example where you start with this data set of two-dimensional features where you can see the data is not linearly separable, but then somehow you do some transformation, you grow this to this third dimension, and now you can pass this plane between your transformed features and you're happy. So you go from linear classification not working to linear classification working. Okay, so that's a high-level idea. Any questions before we move on? Okay, so so I've talked about the feature transformations. Here's basically another example that's a little bit less stylized, but still kind of stylized. So here we have, again, two-dimensional data. And we have the blue points, which are on this inner ring, and we have the red points are on this outer ring. And as you can imagine, if I work with the raw features, there's no way that I can come up with a linear classifier that separates the blue and the red classes. And so that's if I'm working with my raw features x1, x2. But now let's say I have a feature transformation that keeps the first two dimensions the same, but then adds a third dimension, assuming that this is the origin here. It's going to add x1 squared plus x2 squared, right? And basically, that feature, that new feature is describing how far a point is from the origin. And so when I plot the data now according to that third dimension, you can see that all the blue points are close to the origin. So they have, in that third dimension, they have small values. And the red points are higher, they're farther from the origin, so they have larger values, and that means that I could come up with a plane that perfectly separates my data. So just another example of what we saw before, but a little bit more specific. Okay. As you can imagine, the challenge now is, how do I come up with that transformation? Like if I knew my data really well and had a simple form, maybe I can dream up a transformation that's going to work really well. But when I deal with like MNIST digits even, like high dimensional data already, how can I wrap my head around what kind of a transformation is actually going to work for that? And so it turns out people have sort of designed, using smart ideas, they've designed some pretty famous transformations that work pretty well for most data sets, and we'll talk about them. But still, it's like you're choosing from one of a few of these like famous kernels or transformations. And so it's not clear that that's going to be the best thing for your data set. So, but that's just sort of where we are in the progression of the course and understanding the options available to us. Okay, so here the idea is if someone gives me a fee, I can hope that this sort of thing happens, after which my data can be linearly separated using, or can be as linearly separable, and so maybe a linear classifier like SVC is going to work well. That's the high level. Yes?
So the graph on the left where it says data projected R squared, it says non-separable, but wouldn't that be able to be separable through like polynomial equation? Why is it important for it to be like linear?
So it's like if we work with the original features, right? So these are the original features. There's x1 and x2. I think you would agree that that data set is not linearly separable, right? There's no line, there's no linear boundary I can make that separates into blue and red.
Yeah, I guess what I was saying is like, maybe this is a dumb question, like you could form a circle around the inner points and it would separate the inner points.
Yeah, but the way we're doing that is using a feature transformation. So
Oh, so, okay. So
that's the whole point, is like we found a way to start with these two features and grow it to a three-dimensional vector, which we call phi of x, where the first two we kept the same, but what we added is a third dimension that is precisely the radius. And now these are the new transformed features, and now we just do linear classification with that data set.
okay, that makes sense.
Right? So this data set, as you can see, is nice to work with. It's linearly separable. All the methods we've been talking about, logistic regression, SVC, they're all going to work great for this. Zero training error, whereas they would fail completely for this. So this is just kind of illustrating the power of this idea of feature transformations. As long as you know the right one, right? That's the catch. Yeah. Yes?
Is it always the case to keep the original features, or we can just keep
No, usually it's not the case, but here it was just sort of an easy example.
So we can have a lower dimension if you want, at least.
In principle, yes, but in practice, it tends to be higher dimensional. So like if you really knew your data, like in this case, we could go down to a one-dimensional feature, this one, that would work fine. But we really have to know our data set. We have to know how to design that. So what I'm saying is, like, if I give you MNIST, it's not really clear how to design it. So what most of these transformations do is they go into some higher dimensional space where there's just a hope that with all this extra information, you can figure out some way to use it productively in a linear method. Yeah, it's not strictly necessary to go up, but it tends to be what happens in practice. Okay, great. Okay, so let's say that we're doing this now. So someone gives us this transformation phi. And so now, if we look at our SVC equation, it's exactly the same as before. The only thing we've changed, which is highlighted in this red font, is that we have applied the transformation to our training features, right? So this is something we can do like offline as a first step before we're even running our SVC. And once we have this transformed data, we just give it to our SVC. We train it, we learn our W hat and beta hat, the optimal W and B vectors. And now we have to make sure to use exactly the same transformation on our test feature vector x. So we put x through our transformation, we compute the score, and take the sign and so on. And that's exactly the method, right? So all we've done is we've basically we've changed this step here. So this is fine, except when you start thinking about it, and again, like I said, what's typically done in practice is you want to grow your feature dimension. So, so maybe like for MNIST, maybe if you didn't really know a good phi, maybe you would start with, what is it, 384 pixels? I think that's the number of pixels in MNIST, right? So what if I wanted to do like polynomial transformation of that? So now I could look at, 384 pixels, the raw ones, then I could square all the values. Now I have like 2 times 384. But then I could also consider like all the kind of cross products between one pixel and another pixel, like x1 times x2, that's a new feature. x1 times x3, that's a new feature, and so on. And if I do that, I have 384 squared features. And so now you can see the feature dimension is just exploding once you start imagining all the things you can do to try to transform your data. And so as the features are growing in dimension, simultaneously your W vector must also grow in dimension, right? And what do we know happens if I have, polynomial regression with way too high of a polynomial order, right? I run into the variance problem. I have lots and lots of parameters to train. Maybe a lot of those features aren't useful, and I end up, even though my bias goes down a bit, my variance goes up tremendously, and I'm unsuccessful. So those are sort of the issues that you face. Number one, maybe in choosing phi, but then also implementationally, this could take you a long time to run if you have just a massive number of coefficients you have to learn. So, so basically, that's one of the limitations, that we can't just do this without thinking about it a little bit more. And like I mentioned before, it might sound crazy, but what if I want to use some sort of infinite dimensional feature transformation where there's actually an infinite number of these outputs of the phi function? And although that sounds crazy, it's actually the case for the most popular phi that people use in practice. And so we'll learn more about that. So basically, this is kind of one of the issues that we face once we start to think about feature transformations. And so to get around this, we're going to do a couple things. The first thing we're going to do is we're going to approach the problem in a different way. So in the traditional approach, what we do is, we design W and B, right? Those are the parameters we design, and the number of coefficients in W is exactly the number of transformed features we have. It turns out that there is a completely different way to train the same classifier, but it uses a completely different set of parameters. Instead of W and B, which are D plus 1 dimensional, it actually uses these new parameters, lambda, and there's n of them. Remember, n is the number of training points, training samples. Okay, this is known as the Lagrangian dual form of the optimization problem. And in convex optimization, and actually this problem here is a convex optimization problem. In convex optimization, if you take a course, this is one of the standard things you learn. You learn how to solve the problem in the primal domain or the dual domain. There's sort of two different ways of looking at the same problem. And this is just the dual form of that SVC. Now, I can't get into all the details here because it involves a bunch of math that you wouldn't know probably unless you took an optimization course. If you are interested in the details, they're nicely described in section 12.2 of this textbook. So if you've taken the convex optimization course, you can see exactly the derivation of this. But if not, I'm not going to test you on this. Just suffice it to say that there's a different way to solve the same problem. So this is the training step. Notice we're just minimizing now over those lambda parameters. And then once you've solved for the lambda parameters, the way that you do the inference or test step is like this. So you have your test vector, you do all these inner products with your training vectors, and then essentially, you end up multiplying those n values by the learned lambdas. And there's a way of computing the same b hat again, but it turns out that one little thing that's different is this index I hat is any support index, any index in your training set of one of the support vectors. So basically, like I said, You'll just have to take it on faith that this actually solves the same convex optimization problem. But the key point is that by doing this, you never actually train something that has D parameters in it. So that can be good and bad. If I have a situation where I have a very large number of training samples, so N is very large and D is very small, in this case, in the regular version of it here, I'm learning D plus 1 parameters, small number. Over here, I'm learning N parameters, which is a big number. So this could actually take me a lot longer computationally. So in that case, maybe you wouldn't want to do this if all you cared about is solving the SVC. On the other hand, we did see a lab, maybe it was lab 4, it was the one where the data set was, people were wearing, measuring their brain signals, and the number of subjects was the number of training samples. It was on the order of hundreds, but the number of voxels in the brain was 30,000. And so in that case, the number of parameters here was way larger than this. And so if you just want to solve the SVC there, this would be a way more efficient approach to it. So it really kind of depends on whether you have more features or more training samples, which one is more efficient, but they should give you the same answer as long as it's implemented correctly. So just two different approaches to the same problem. But the key point is that this one bypasses the computation of W hat, and maybe you can see where this is going here. We said that W hat is really the limitation that you face when growing the dimension here. So if I never have to actually design a W hat, then maybe I can let the dimensionality of this grow as large as I want. And that's sort of the intuition. Okay, so anyway, this is the Lagrangian dual formulation of the SVC. Are there any questions on this? I realize I didn't give you much to go on. But okay, so, and it turns out that the logistic regression also, you can do the same thing with logistic regression. It's not done as often, but this is very often used in machine learning, the Lagrange dual formulation of the SVC. Okay, so now finally, let's put all our pieces together. So we're going to use the dual form in the SVC, and we're going to use the transformation phi of x. So basically, all I'm doing is I'm taking these equations on this, but wherever I see x alone, the untransformed, the raw features x, I'm just going to replace them with the transformations of my function phi. And what's interesting is that, this is what you do for, this is test. This is training. This describes everything you're going to ever do. You can see that you always have a situation where you have phi transpose phi. So what changes is here you have the ith training sample, you have the test features. Here you have ith training sample and then one of the test features. Here, ith training sample, jth training sample. But the point is that you never see phi alone. You always see phi transpose phi. And phi transpose phi is just a scalar, right? So even if phi has a very high dimension, it's kind of like something that is just maybe implicitly used or used if you explicitly actually use this phi function. So instead of doing that, maybe we can just replace wherever we see this, just think of that as some scalar output function kappa that takes in two different x's. The x used in the first case and the x used in the second case of phi. And so now, basically what we're saying is this would just be kappa xi comma x. This would be kappa xi comma xi hat, and this would be kappa xi xj. And now, let's not even think about phi anymore. Let's just define what kappa is. and forget about phi. And that's what's called the kernel trick. So you work exclusively with the kappas. Given a kappa, you might even wonder, what would the phi be that gives me that kappa? Maybe you don't care. Maybe if you have a kappa that works well, that's all you care about. That's all you need. And that is actually, so that's how it's done. We want to come up with good kappas, and then we run this algorithm like this, but with the kappas alone. Never actually compute phi, never learn any parameter vectors whose dimensionality matches the dimensionality of phi, because phi is just never used. Okay, so that's the kernel trick, and the question remains, okay, so what are the kappas we're going to use? So the ones that are the most popular, the ones that are in scikit-learn, are these four. What's in common among all of them is that they all measure essentially a form of similarity between x and x prime, meaning the more similar x and x prime are to each other, the larger the value that kappa outputs. So for example, the most similar x and x prime could be as if they're the same, right? And that's when the kernel output is the largest, and as x and x prime get more and more different from each other, the kernel gets smaller. And every kernel has its own form and therefore its own definition of similarity. So the RBF, radial basis function kernel, is by far the most popular one. And this is the form it takes. You just compute the 2 norm between x and x prime, the two different x's, the 2 norm squared. You scale that by negative gamma, and you put that inside an exponential function. Okay, so it's not really that much work to compute. Basically, if you have d features in x, basically it's just like, d, you square d numbers and you exponentiate their sum. And like I said, that one is the most popular. That really works super well. There's other options. There's like this polynomial one where you compute these inner products between x and x prime, and then you scale them, you add an offset, and you take them to some power d. All these parameters are things you must choose. You must choose gamma, you must choose r, you must choose d. Another one is the sigmoid, where it's like the polynomial one, but you put it inside a hyperbolic tangent. And finally, another one is, maybe the trivial one, is the so-called linear kernel. This corresponds to just doing no transformation at all. So in this case, the kernel would just be, x transpose x prime. So this one is really just going back to the linear SVC that we studied earlier. We don't expect that this will work super well unless the data is linearly separable. So for non-linearly separable data, we would hope that one of these other techniques here, these other kernels, is going to work a lot better, and they do. Okay, so those are sort of the most popular kernels. Are there any questions about any of those? Okay, so another nice thing about the RBF is it only has one parameter, this positive parameter gamma, but it is important to tune that. Okay, so another interesting thing about this RBF is that there's a strong connection to infinite dimensional polynomial regression. So if you want to learn the details, you can click on this link. I'm not going to get into it, but basically there is a connection there. And another, so here, like I said before, it's infinite dimensional, meaning that if you try to figure out what is the phi that corresponds to this kernel, you can deduce that this, whatever phi that is, it has to have an infinite dimension. So it's something that you couldn't actually implement on its own, but you can implement phi transpose phi this way. And then get the benefits of that infinite dimensional phi using this kernel trick. Okay, so that's the kernel trick. If there's no questions, let's just briefly talk about implementing this in scikit-learn. So in this case, we're going to use svm.svc. Like I said, the kernels available to us are the ones on the previous page, or you can program your own custom kernel, and you can just give that like as a function handle to the method. You do have to specify the kernel width. As before, you have to control the number of support vectors with that C parameter. And so really, you have to jointly optimize those two things. So this is a little bit of a pain because you have to do a two-dimensional grid search. And every point in that grid search, you're working with this, maybe kind of complicated loss function, and it just takes a while computationally. So that's one of the downsides of this method. The training complexity is on the order of, actually, let me put a little d in there, d times n squared. So d is the number of raw features, 384 in MNIST, and n squared, you can see it grows quadratically in the number of samples in your training data set. So as your training data set gets larger, this starts to grow very quickly in complexity. If you think about logistic regression, it's actually dn without the square. So this method, as your data set grows, just takes a lot longer than logistic regression. Test complexity is going to be d times the number of support vectors. So even when you just want to compute the prediction from a single feature vector x, you actually have to access all the support vectors for your data set. And if you have a big data set, there could be a lot of support vectors. And you have to do these inner products or, RBF two norms between all your support vectors and your test x. And so even just computing the output from a single prediction can be intense. It can take like a minute as you're waiting for your laptop to run. So it's a little bit of a pain. But the reward is that the performance is significantly better than the linear methods we tried earlier. So if you remember, it was 90.7 with the linear SVC, and now, once we bring in this RBF kernel, it goes up to 97. So that's like a massive increase in performance. This is where we see this big gain happen. And for this demo, I didn't actually use all the MNIST samples. I just used, I think, 10,000 just to speed up the process. So, we could probably do better. And if you remember in the table I showed you at the beginning of the unit, I think it was like 1% accuracy for if you do everything right on MNIST with this support vector machine. Okay, so that's kind of the end of the story here, at least for the binary case. Any questions on this? Okay, just a couple more things to talk about. Okay, what if we do the multi-class SVM? It turns out that this is where it's going to use the 1 versus 1 approach that we talked about earlier. And this is because, in part because of this quadratic growth in complexity. When you do 1 versus 1, you end up using a smaller training data set for every one of these boundaries. And so that quadratic complexity hurts you less. You have more pairs to train, and so there is that side of it. But I think this is why they use the 1 versus 1 approach. Otherwise, the interface is exactly the same whether you have binary or multi-class. One other thing is that there's a different way to set up the problem where instead of this tunable parameter C, you have a tunable parameter rho that is somewhere between 0 and 1, and that is called the new SVC. And it should give you the same result as the original SVC. So for every C, there's exactly one new that corresponds to it. But this C is a little bit harder to tune because this could be a possibly very large number, so maybe you have to search over many orders of magnitude, whereas this new is just a number between 0 and 1, and it's easier to find it. and it has an interpretation, which is it's a lower bound on the fraction of support vectors. So it's more interpretable. So whichever you decide to use, the new SVC or the regular one, you should get the same result more or less. It's just a matter of tuning it is a little bit different. And you might actually have like a guess for how to start based on the fraction of support vectors. You can sort of build your grid search around that. Okay. All right. Any questions on that? Okay. Very last thing is we can actually use these ideas for regression as well, not just for classification. So the way that this is typically done is, so usually in regression we think about maybe putting on like a quadratic loss. We say, let's look at the difference between yi and y hat I and square it, and we want to minimize that, right? We've also talked about putting absolute value loss and saying that might be more robust outliers. That would give you like minimizing L1 instead of L2. Well, in the support vector regressor, basically you say like, I'm going to tolerate small errors. So if my errors between my predicted and true targets are within minus epsilon to epsilon, where epsilon is some small positive number I choose, I'm going to say that there's no error at all. I'm going to say that's fine. But outside that, I'm going to do like a linear penalty on how far that deviates from epsilon. So here's like how to picture this cost function. So this would be like y minus y hat. So as long as that is between plus and minus epsilon, you say there's no cost to that. But then as that difference grows beyond epsilon or below minus epsilon, you have this like linear penalty. And epsilon is actually something you have to specify. It's just one of the things you got to tell it. So basically, if you want to do this, the hard margin regressor looks like this. It's minimize this term just like we saw before. All that changes is the constraints. Minimize this such that your errors are somewhere between minus and positive epsilon. And so, of course, that works only if there exists some B and W that can provide that behavior. If not, then you can take these inequality constraints and convert them to a cost, and then you get this cost. And this term here is exactly this thing I plotted down here. It's called the epsilon insensitive loss. So now, following the same pattern as we saw with classification, instead of the primal formulation, we can use the Lagrangian dual formulation, and we can use a feature transformation, or even better, a kernel, such as the RBF. And that's when you start to see the performance of regression be way better than linear regression, because you have that feature transformation implicitly done by your radial basis function, and can work way better. So basically, the story is very similar to the classification. You have essentially the same kind of functions. You have the linear SVR that solves this problem. You have the usual SVR that uses Lagrangian dual with your choice of kernel, and you have the new SVR that uses, instead of C, uses that new parameter. So that's all we have for this unit. Let me know if you have any questions after class, and otherwise we'll get started on the next unit on Friday. See you guys then.